Okay, so we're going to start our second part of modern physics, and it's going to be about what goes on in the nucleus. So the nucleus was discovered by Rutherford. In the Guilfoyle experiment. Okay, and he found that the nucleus is tiny, dense, and has a positive charge. Later on, at first, with the Guilfoyle experiment, the alpha particles he was shooting at Guilfoyle weren't going fast enough, didn't have enough energy to penetrate the nucleus. When they could get them to higher and higher energies, they could start to penetrate the nucleus, and found out that the nucleus is made of protons and neutrons. So it might look something like this. So something like that. Now, the question is, why doesn't the nucleus fly apart? Okay, the protons should repel each other. So, based on what they knew at the time, there's no way that the nucleus should be able to hold itself together. So they postulated something called the strong, or the nuclear force. And it has two properties. It's strong enough to overcome the electrical repulsion but it only lasts over a very short distance. About 10 to the minus 15 meters. And that actually puts a limit on the size of nuclei. If you get a little bit bigger than 10 to the minus 15 meters, then they're going to fly apart because the strong force doesn't work any farther. So if you think of all the naturally occurring elements, you get up to about an atomic number of 100, and anything beyond that won't occur. It turns out that the strong force is one of the four fundamental forces that make up all forces in nature. Okay, so you need to know what the four forces are and a little bit about each one. So the first one that we studied was gravity. The extent of gravity is infinite. It reaches forever. It's 1 over r squared type of term. So as you get farther and farther away, gravity gets weaker and weaker and weaker, but it never falls off to zero. This works on anything with mass. Fg is g m1 m2 over r squared. It turns out it is very weak unless the masses are huge. Okay, so any two masses will attract each other. You can know that too, that it always attracts. So any two masses are going to be attracted to each other by the force of gravity. We don't think about it in normal type objects like a textbook and a pen sitting near it. There is a force of attraction between them, but it's very weak. You couldn't measure it. The second one that we studied is the electromagnetic force. The extent of that as well. It's also a 1 over r squared force. Works on charges. And its F is K Q1 Q2 over r squared. Okay, so it's very similar to gravity. The third one we just talked about is strong, or the nuclear force. The extent is very short, about 10 to the minus 15 meters. Works on nucleons, meaning things inside the nucleus, protons and neutrons, and it holds the nucleus together. And it is very strong. Okay, but only for a very, very short range. And the last one we don't need to know much about, but it's called the weak force. Okay, it is also very short. Works on nucleons. And it affects radioactive decay. And you really don't need to know much about it other than the fact that it exists. But all forces in nature are made up of these forces. If we think of a normal force, it's actually an electrical force. It's the repulsion between the electron shells, say, in the table, and my hand pushing down on the table. Top of the next page. Now, when they started to work with nuclei and be able to measure them very, very precisely, they found that in nuclear reactions, mass is not conserved. Okay, at first they probably thought they were making mistakes. They weren't measuring the masses accurately enough, but it turns out that they were always missing some mass, and they decided that this was a real thing that was going on. So one of the biggest rules in chemistry is mass cannot be created or destroyed, but in nuclear reactions we do see it. Okay, so the missing mass or the mass defect is turned into energy. There's two ways to calculate it. One is Einstein's famous equation, E equals mc squared, where mass is in kilograms. The energy is in joules, and c is the speed of light. Okay. The other way to calculate it is if you have your mass in atomic mass units. So 1 atomic mass unit. They use the symbol U for that. Turns into 931 MeVs of energy. So if I have my mass in atomic mass units, I'm going to just multiply by 931, and that'll give me the energy in MeVs. Now, how much energy would be created if 1 kilogram of matter was destroyed? Okay, so if we're in kilograms, we can just do E equals mc squared. So it's 1 kilogram times 3 times 10 to the 8 meters per second squared. And that's going to give me 9 times 10 to the 16 joules of energy. That's a lot of energy. If I was to write it out, it would be 9, and then 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16 zeros. Okay, so it's that many joules of energy. So if we could destroy 1 kilogram of matter, we would get tons and tons and tons of energy out of it. So this is how nuclear reactors work. Okay? In that nuclear reaction, whether it's fission or fusion, you are losing some mass. When you lose mass, that mass gets turned into energy. So just a little bit of mass can give you a lot of energy out. Now, in a second example, a neutron decays into an electron and a proton. The masses of them are as follows. Okay, and we want to know how much energy is created. So our product have masses of 1.007276 U's plus 5.48579 9 times 10 to the minus 4th joules. I add those together, I'll get a total mass of 1.007825 joules. The reactant, okay, is just the neutron. The mass of that was given up here as 1.008665. So our mass defect, or our missing mass, is 1.007825 minus 8665. And that's going to give me a missing mass, there's a value around it, of 0.00084 joules. Now, if I want to find out how much energy that is, I'm not going to use E equals mc squared, because I do that with my masses in kilograms. If my mass is in atomic mass units, then I just multiply it by 931. So my energy is going to be 0.00084 times 931 MeVs for each atomic mass unit I destroy. And what I get when I multiply those together is 0.782 MeVs. And that is an energy unit. So I don't need to do anything else with it. I could convert it to joules, but they're not going to ask you to, probably. They're just going to say, what is the energy in MeVs?